first of all, welcome to the seminar, to this webinar. We will be focusing on our internally developed Elaphe principle of designing and validating in-wheel motors in order to basically get them to be as robust and safe as possible. This will be looked over holistically. However, the focus, as Tiasha said, will be more in the structural, thermal, and durability sense. And maybe before we go into the details of that, some of you probably already know us, but maybe some don't. So a few words about the company. So the company was founded in 2006. However, the development already began in the late 80s. But from 2006, the more production-focused development, as well as a significant improvement to the performance of the motors was started, and basically, let's not say perfected, but improved up till now. So for the last 15 years. And basically where Elaphe is today is we offer a full system that includes multiple wheel control. We have validated the motors on different benches as well as 100+ vehicles. We have some customer launches, and we are over 150 people, employees, with a global presence in the US market, China market, and where headquarters is in Europe. And having a long legacy of R&D, we also have lots of innovative patented solutions, which keep on increasing in number. Well, you probably are familiar with in-wheel motors, but maybe let's just discuss a few benefits that in-wheel motors actually bring to the whole vehicle architecture and to the design, as well as the vehicle, let's call it mission profile. So what you get with in-wheel motors is a true freedom of design. So there are no drive shafts, which enable new vehicle layouts. You can get a flat floor and maximize the space inside the vehicle for passenger comfort, because basically all of your propulsion is in the wheel where it's needed. You don't have any gears, which also lowers mass, and with lower mass and less losses in the gearboxes, you can extend the range of the vehicle. What is also kind of unique to Elaphe in-wheel motors is that it feeds standard parts already existent on the vehicles. So there is a real ease of integration, and there are less spinning parts, so there is less complexity and maintenance. But perhaps what most important is enabling torque vectoring, because you have true independent wheel control with really, really fast response times. So those were a few words on why it's good to have in-wheel motors, but let's talk about all the challenges that we had to successfully overcome over the years that are present due to the location that the in-wheel motors are at. So the motors being in the wheel means that the loads acting on the motors are quite different to typical onboard motors. And when we started this, there were no typical standards for in-wheel motors. There were no tests for in-wheel motors. So we had to take a step back and look at this from a holistic approach and design new innovative approaches, basically to get to our internal development principles in terms of design and then also in terms of validation. So talking about the in-wheel motors and the differences compared to an onboard motor or a central motor, we have to look at what are the challenges. So what is different? And basically with the motors being in a more direct contact with the ground, we of course need to have a durable construction. as well as there is an air gap as with any electric motor. So there is a requirement for high stiffness, which includes bearing stiffness as well as motor component stiffness, which is achieved by different topology and other optimizations of the motor components, as well as good understanding of the bearing and setting the requirements on the bearing correctly, so that they're applicable for the vehicles that the motor is being designed for, as well as the motor where, based on the location, also the thermal elements of the motor are quite complex because it's totally exposed to the environment. So from really cold temperatures to really hot tarmac temperatures, there are different conditions that the motor needs to safely operate within, as well as there are some electromagnetic losses of the motor and basically some residual torques, as well as brake heat generation. So accurate thermal mapping is required. In a short summary, what this means is that, like anywhere you wish to have a stiff and durable yet lightweight and compact construction. So basically you're like in aerospace industry, and that's the ultimate wish of I think any engineer. But what have we at Elaphe taken as an approach on designing this is first to understand really what are the loads that are acting on the motor. So doing this, we kind of separated the loads in two general groups. So one are what we call external loads, where you have a subgroup called inertial loads, which means loads coming from the motor's own weight. And these loads are, for instance, vibrations, shocks that are acting on the motor. And then you have road loads, which are kind of different. So you are basically loading the motor assembly, let's call it like that, the same way that you are loading any corner on a typical current on the road production vehicle, but without those loads stressing the motor. So how is that achieved? It's going to be shown a few slides later. But what is important is that during such scenarios, the motor has to operate safely and normally, and this has to happen several times in the lifetime of the motor. Then also, as with any other motors, you have different internal loads from manufacturing loads, assembly connections, because you have to build the motor somehow, as well as thermomechanical loads. So these are loads that happen due to the combination of different materials and the difference in the thermal expansion of those materials, where I mentioned that the environmental conditions are vast. So the range is vast, and this becomes important. The motor also takes different shapes, and we have to account for the extension and expansion and compression of the motor. And there are also electromagnetic loads, such as the EM torque and the electromagnetic force due to eccentricity, which is trying to pull the motor and the rotor together. So after we've identified those loads, we kind of had to look at what would be the best possible layout of the motor so that these loads influence the motor design the least possible. To do that, we need to look at the typical Elaphe motor layout. So if we look at the vehicle corner, we have the suspension and a typical standard knuckle for the vehicle. And what we do is we attach the motor to that knuckle. So this means that actually the stator of the motor is attached directly to the knuckle, as directly as possible, with the bearing to follow, and later on followed by the brake disc, the motor rotor, and a standard rim and tire. This basically allows us that the only thing keeping the motor and the stator and the rotor apart is the conventional hub bearing, which is basically performing the same function as one would expect from a caliper and brake rotor point of view. So the stiffness is already looked at, the stiffness of the bearing is already looked at for the purpose of keeping the brake rotor and caliper apart when going into a corner, because of course you do not wish to brake when making a turn. So in the same way that you don't wish the brake rotor and the calipers and the braking pads to touch, the same way, well, when not wanted, the same way you don't wish the motor rotor and the motor stator to touch. So our typical design of the motor is a synchronous motor with permanent magnets, which means that we have the surface mounted magnets on the rotor. And there are the static components, so the active part on the stator, and there is a small tight air gap between the two, which needs to be maintained during all different conditions. What are the benefits of having such a design? Well, basically, no loads get passed through the motor, only through the central area where the bearing is, and the rotor and the stator kind of act as cantilevers outside of the load path. And this will be shown more in the following slides. However, as mentioned before, the bearing stiffness is really important in order to achieve this. So that's usually one of the first steps during our design of the motors. So it's to understand the different possibilities for the bearing what we operate with. So in order to achieve that, we have an internally developed analytic bearing calculator, which calculates the stiffness of the bearing and the stress distribution on the bearing elements. And we use that in combination with FEA to get as accurate bearing stiffness predictions as possible. And then basically those same bearings have to get tested at a later stage to get to the numbers of the actual bearing deflection. So what does bearing deflection means? It's basically how much does the bearing bend during a bending moment. So how much does one flange of the bearing compared to another deflect? When performing the tests, we also had to do several correlations with the analytical calculator and the FEA to improve our models so that with each following iteration, this gets more accurate and more robust. So we started this from a design perspective of what would the ideal design that be for the motor to withstand the loads as much as possible, so to be as robust as possible. So we had to identify the load transfer path, which I described before. So it's basically going from the contact path between the road and the tire, through the rim, through the bearing, through the knuckle, to the suspension, and to the chassis. So the motor components are with this not loaded to scenarios such as this. And this is really important because well, we drive our cars a lot, we do lots of corners, and if you would reduce the integrity of the motor with doing lots of turns, that wouldn't exactly be an ideal design. And this enables us to make the design as lightweight and to focus our let's say, development on the electromagnetic components, so to achieve the best performance. Here in the middle, you can see that we also have to take this into account with the simulations. So after we get the correct bearing stiffness information, we have to model that. We have to basically recreate the loads that are happening on the vehicle also in the virtual world, and address them appropriately, so that we also get all the information about the formations on the motor, basically from the deflection point view of the rotor towards the stator. And when we do this, we try to incorporate as many of the surrounding components as possible to get an as accurate stiffness of the whole system as possible. Once we do that, of course, we also mentioned validation. So we started with phase more. We use standards in different methods to account for this from design validation. So we basically took different standards for rim testing, for bearing testing, and we applied them to the whole motor configuration. And as I mentioned, that this is really important from a design perspective, and also air gap stability perspective. We have to monitor that air gap at such tests, so that we know that the design, so that the behavior of the motor or the motor air gap is as predicted. Final confirmation, of course, has to come during vehicle design validation, because you can predict this to a certain extent, but actual vehicle usage is the important factor to this, and we are expanding on that area as much as possible. And also, as mentioned, with the bearing, also doing back correlations with simulations and calculations to get as accurate predictions in further iterations. So a lot of the usual questions about in-wheel motors are what happens during the pothole. So similar to cornering, no forces actually pass through the motor. So the forces go the same way, so they follow the same path from the tire, through the rim, through the bearing, to the knuckle, to the suspension. So no direct stress is imparted on the motors from a force perspective. However, there are some shocks that occur during such scenarios, and this is due to the motor's own weight, and these shocks are then covered separately. So basically, you can either, to put this really plainly, you can either simulate this as a complex scenario, or you can, so a dynamic scenario, or you can do this in a quasi-static approach. So to first identify all the deformations that occur to the motor and surrounding components, if they're strong enough, and separately from a quasi-static approach, also try to identify correctly the stresses due to the motor's own weight and the shocks that are passing through them, and then combine that, which is actually what is then validated during tests. So a combination of both, so these direct scenarios, where this can be seen on the next slide. Action test is very different bearing standards, both from a frontal impact area, as well as from a lateral curve effect. So like scenario. That being said, you can predict, but these are still misused. Basically, if some of the users were to exceed our expectations, we would still want for the motors to be as intact as possible and to operate as normally as possible. So as mentioned, one of a pothole scenario is something that is easier to accommodate with the motor design, with being as stiff as possible, and to ensure that during shocks the motor doesn't deform in order to to the levels that would compromise the motor integrity or any of the functionalities. However, the curve strike scenario is something that is more difficult, because as mentioned before, the only thing keeping the rotor and the stator apart is the hub bearing. So if the hub bearing would deflect too much, of course, you could expect some contact between the rotor and the stator. So in order to mitigate that, so if you exceed the expectations of the design that we set out as the requirements for the design, basically we can still allow the motor and the stator to touch. However, it has to be outside the electromagnetic area, which means that the motor damage is minimized, and with this, its functionality is not impaired. So no degradation of life or performance can be expected if it's designed correctly. So as mentioned several times during the pothole scenarios, we also have different shocks and vibrations acting on the motor due to the motor's own mass. So it's kind of, we call it self-excited loads. And with the motors being where they are, these accelerations and shocks are quite different compared to typical onboard motors. So we differentiate this into what we call deterministic shock loads and vibrations which are random vibrations, where we use power spectral density for fatigue evaluation of the material. So how does the material integrity degrade with time has to be taken into account, because there are a lot of vibrations on the roads. As well as talking about axial shocks. So we usually go for 100 G, axial shocks, radial shocks, longitudinal shocks, where we take a look at the different stress levels occurring on the motor, as well as the deformation of each and every component, in order to ensure that during such scenarios, the motors can operate safely without any degradation to the motor performance during or afterwards. So as usual, we also test this first on the motor level. So you can see what the mechanical shock test looks like on the left. So it's a repetition of dropping the motor and decelerating it in a controlled way to get to a 100 G acceleration on the motor level. You can see also the random vibration PSD fatigue test. This is a multi-axial test where the motor is excited in all its axes, as well as thermally in different conditions. And it's an accelerated test, so that it encompasses the whole accumulation of vibrations happened during the vehicle and the motor lifetime. So this, as mentioned, is a real test for the fatigue strength of all components in the motor. And as mentioned before, these are mainly these are tests that are based on different standards that we had to combine, and basically sequence in certain design validation flows to get a representable design validation plan, so that it actually encompasses all the different aspects of let's call it aging and basically aging of the motor. So the next set of internal loads that occur to the motor are torque-based loads. So of course, an e-motor being what it is, it creates torque. But the influence on the motor design due to the torque is usually small. Well, there is also the mechanical braking torque that occurs. And the design being such as it is, this doesn't load the motor. However, both generate heat, and that heat is important for thermal integrity. So what we had to do is get a good understanding of different thermal fields that occur on the motor during such scenarios. So we had to do braking tests with different thermocouples or thermistors to get some thermal stickers, etc. So to get an accurate thermal map of the motor during different braking events. We also recreated this in parallel using FEA and correlated this so that we have this as parametric as possible, as well as to get an accurate understanding of how does the thermal field change if some of the environmental conditions change as well. So once we have an accurate understanding of the motor integrity in terms of braking torque, so in terms of the heat generated by the brakes, that is also incorporated in simulation of the thermal field of the motor itself, where the thermals of the motor due to the motor losses, so self-heating of the motor at different conditions is taken into account. So how do we actually achieve this is we have a comprehensive workflow for evaluating this thermal integrity with simulations. So from electromagnetic magnetic FEA, we also use a coupled approach using the electromagnetic properties of the motor and the losses that are occurring on the motor and changing with temperature to incorporate them correctly in the thermal FEA of the motor to get an as accurate thermal understanding of the motor as possible. And we have come between tests and simulations to an accuracy of within 5%. And you can see a configuration of how the motors are tested. So this is actually a picture of the motors within a thermal chamber. So this thermal chamber then goes to the minimum motor temperatures, usually being minus 40 degrees to degrees centigrade to a maximum of usually 85 degrees centigrade. And this is cycled for many times, as well as loaded using different torque and power requirements to thermally basically load the motor and age the motor as much as possible. So when we've done all of what was explained up till now, we still have to address the mechanical air gap stability from a way of combining all of the different aspects together. So imagine when we were discussing cornerings, this is usually done when the motors are lukewarm, so normal operations, the ambient temperature is as well normal, so probably like 20 degrees. But what happens if you, for instance, go driving in the desert, on a racetrack, something like that? Well, basically, we need to understand the motor, so the mechanical air gap stability, if all of those things are combined. So to the road loads and inertial loads, we have to also add the electromagnetic forces that occur due to stator eccentricities. So basically going into a corner adds changes that force of the basically pulling the rotor towards the stator. There are also different assembly loads and the different thermal mechanical behavior of the motor due to the torque application or braking, etc. So there is an expansion of the stator in regards to the rotor, for instance, and this needs to be taken into account at the same time, as well as the whole tolerance stack of the motor, so and all the surrounding components. So this means that all components in there have an influence on this, and if they were designed, they were produced ideally, this would be unimportant. However, everything's produced within in certain tolerance ranges, so this needs to be taken. This needs to be looked at carefully and summarized in a systematic way, as well as with the influence of all the before mentioned, to actually get to a stable air gap. So it's a long process, but if designed correctly, it ensures a long durability of the motor and a lightweight design. So there is also an aspect regarding the environment itself. So we need to address the environmental protection of the motor during all of those different conditions that I mentioned. So using DFMEA, we've addressed this as closely as possible, and we've updated that DFMEA throughout the years. So we have a really vast, let's call it DFMEA library. It's one of the cores to our designs. And we addressed, we basically subject the motors to a salt rate test, to a salt water immersion test, ice breakup test, where the motor and together with the rim and everything is covered in ice and it has to break free of the ice. There are salt mist tests, mud immersion tests, as well as different thermal tests. So as mentioned before, where the motors are in chambers and subjected to different thermal and environmental conditions. Once all of that is done, as mentioned also before, and I maybe keep repeating myself, but all of these needs to be repeated on the vehicles. So vehicle validation is important, and now I don't. Wait, things aren't. Okay, give me a second. Sorry, I'll have to reopen the presentation. I apologize, but it's a large file with lots of nice pictures and videos, which apparently PowerPoint doesn't agree with. Okay, so as I was explaining before, all of this needs to be tested on the actual vehicles themselves. It's an important step which allows us to get a better understanding of the loads acting on the motor, as well as a better correlation and possible improvements to the design. We've been doing a lot of that, especially in the recent years. with our own vehicles as well as several custom vehicles. You can see on the top left where we have a vehicle track driving, so where we achieve high lateral Gs in order to check the air gap stability as much as possible, whereas also the motor, because of the high power demands, is heated up as much as possible so that it gets to a worst case of a scenario as possible. You can see winter testing below and rough road winter driving in the middle, as well as rough roads, rough terrain driving up top, as well with one of our customer early prototypes, and then some of the customer vehicles, which address also driving in the rain, and advanced dynamic controls of the vehicle during such conditions to address the vehicle stability as a whole. And as mentioned before, this is something that is really important for us. It gives us confidence in what we're doing and that we are addressing the right loads for the motors and basically doing the design correctly to ensure that the motors are as robust and as safe as possible. And we are not doing this for the motors to last a couple thousand kilometers or a couple 10,000 kilometers, but really to last the whole vehicle lifetime. So a general conclusion to this would be that the in-wheel motors can bring key benefits to today's and future mobility with innovative design approaches to the whole vehicle architecture. And in order to develop the motors for such vehicles, a new methodology for design and validation can be developed, which encompasses load identification and guidelines for simulations, adaptation of different standard tests, and a holistic motor validation plan, which encompasses those tests in a systematic way. So the end result is an in-wheel motor that's capable of withstanding severe driving scenarios and extreme environmental conditions. Okay, I was a bit long, but still, I think I hope you got a lot of information. I do imagine, however, there are some questions. So with that, I would like to thank you and open up the Q&A session.